Correlations for the estimation of heat transfer coefficient on film condensations on horizontal tubes are similar to the vertical plate. So let's assume we have a horizontal tube, cylinder or spheres, and with the different temperatures Tsat. So we're going to have a film of condensate forming there and then dripping from the bottom part. So this is going to be the condensate film that is forming here on the outside of this cylinder or the spheres that we have. And the condensation, the Nusselt number of D is going to be HD times D over KL. So the diameter of this cylinder or the sphere is D. So this is going to be C rho L G rho L minus rho V, this H prime FG D3 divided by mu L KL Tsat minus Ts to the power of 1 over 4, where C is 0.729 for tubes, for cylinders, and C is 0.826 for spheres. Now, for the condensers, like when we are designing condensers or condensation heat transfer equipment, it's very normal to have the stack of this tube like vertically aligned. So if we have vertically aligned tubes with a continuous condensate sheet. So what I mean by this continuous condensate sheet that's happening, so let's say we have these tubes and the condensers can have multiple of them. So many on the vertical and then on the horizontal that the vapor is getting exposed to that, to this system. Then we are going to have the condensation build up here, and this condensation is just going to go to the next tube and then it's keep adding up. So you would, and that happens for all of these tube. Now, the first tube at the top, since it has less thickness of the film, it has the highest value of H, and this one has the low value of H. So the H is just keep decreasing when we are coming from top to bottom. Now the heat transfer is going to be HD for the top tube times N to power of N. So this HD is what we are finding here from the top correlations. This is for the top tube. So this is heat transfer coefficient for the top tube, and N is the number of the tubes that are stacked vertically. So let's say this just goes, and this is N from 1 to N, and N, the power of a small n here is, we are getting mob minus 1 over 4 from, if we follow Nusselt analysis, but from empirical, from experiment is 1 over 6, minus 1 over 6 is more appropriate, It has a better match with experimental data. So this is an empirical value. So this is the condensations on the horizontal tube, single tube, and the stack of them, multiple one vertically on top of each other. The last topic here is condensation inside horizontal tube. So what we do here is, if we have a flow, like flow of this vapor that is getting condensed inside the tube. For the low velocity one, what we would expect to see here is if we have a for low velocity vapor flow. And how we decide that one is when the Reynolds number for the vapor, and I means inlet, is evaluated based on rho v u m and v, the average velocity for the vapor that's coming at the inlet times diameter of the pipe divided by mu v. If this is at the inlet I, if it's less than 35,000, then what we would expect to see here is, if I just look at the system, we're going to have this condensate and then a condensate build up here too. So the condensate is just going to be around the surface, but mainly it's going to be accumulated at the bottom. So we're going to have a thicker one. So if I look at the cross section of that, this one, what we are going to see is, see this condensate kind of like building up here. So this is going to be condensate and this is going to be vapor. For this system, we use exactly the same correlations that we have for the vertical one with the minor differences. So here C would be 0.555, and definition of H prime FG, we're going to have a less here one, so FG plus 0.375 CPNL Tsat minus Ts. So this is for the low velocity of the vapor. Now, if we have high velocity vapor flow, which we can find from the Reynolds number, then we would have turbulent system in the pipe. So the way that we would have the condensate and vapor distribution here is we would have a thickness of film of the condensate that is building up on both sides. So this is going to be condensate film for both sides of the, for around the tube, and then we are going to have vapor flow here. Did I mention here? No, vapor flow. And both of them can flow here anyway. So we're going to have vapor and flow. And the way we find this for this system is the Nusselt number D, which is HD H times D over KL is going to be 0.023 Reynolds number D and L to the power of 0.8, Prandtl number of L to the power of 0.4 times 1 plus 2.22 divided by x of tt to the power of 0.89. So how do we define Reynolds number? Reynolds number of D and L is going to be 4 m dot 1 minus x divided by pi d mu L, where this capital X is going to be the vapor fraction to the liquid fractions that we have. Okay, so this is mass fraction of vapor in the fluid that is passing, and this xtt is going to be 1 minus capital X divided by X 9 rho V rho L. So it's quality actually x 0.5 mu L over mu V to the power of 0.1. So this is for the flow that's getting into the flow inside the tube. To use this equation, all properties are evaluated at Tsat, and this equation is recommended when the mass flow rate at any cross-sectional area is greater than 500 kilogram per second. Now, when everything is just a liquid flow or the condensate flow, what it means here is we don't have any mass fraction for the vapor, so x is equal to 0 or xtt goes to infinity, and the above equations for the Nusselt number is reduced, or Nusselt number of D is reduced to this Volter equation except Prandtl exponent. This is the case when we have only the single phase liquid flow. Phase liquid convection. The heat transfer inside the tube can be enhanced by adding fins inside the tube. So we would have more surface area provided for the condensation.